welcome back. In today's lecture, we are going to describe Maxwell's relation. So, Maxwell relation is based on the fact that order of differentiation is unimportant for analytical function. Okay, so which essentially means that let us say if we consider a function f is equal to f of x y, and consider this to be a smooth function, then it is based on the fact that the order of differentiation is unimportant, and in the way we are saying the following. Okay. So, Maxwell relation will be developed based on this simple equality of these terms. Okay, and this also can be written as follows. I can write this as del by del x constant y, del f by del y constant x, and this is nothing but del by del y constant x, del f by del x constant y. So, it clearly tells you this, that the order of differentiation is essentially does not make any difference. So, this is based on the mathematical equality of that these two expressions. Now, based on this we are going to develop four important relations which are going to be extracted from our basic fundamental thermodynamic potential relations in the differential form, and I am going to now write this first. So, let us look at u is equal to u s v. So, we are considering closed system for illustration. Okay. The other thermodynamic functions are h is equal to h function of s and p, a is a function of t and v, and g is a function of t and p. Okay. So, I have not put any n, considering that n is not changed because of the closed system. Okay. So, this in the differential form can be written as du is t ds minus p dv, dh as t ds plus v dp, dA as minus s dt minus p dv, dg as minus s dt plus v dp. Okay. So, these are the four expressions, and now the way Maxwell relation is developed is based on a simple exercise. So, let us say if I can write dz as where we are considering z is equal to function of x and y, then this is something we can write where m is nothing but del z by del x constant y, and n is nothing but del z by del y at constant x. Okay. Now, based on this exercise, what I can write is the following. I can write del m by del y x is nothing but del n by del x y. So, this is nothing but the same expression which is here. Okay. Now, use or apply this particular equality or this particular expression on these four different relations, okay, thermodynamic relations. So, let us consider for the case of u. So, what we are going to have here is the following. It's going to be like del square u, okay, divided by del s del v is nothing but del square u del v del s. Okay. So, this is based on the same whether you consider in this form or you consider in this mathematical relation. So, you can apply this and you would be getting this first relation. Now, I can simplify this relation. I can say this as let us say this is can be written as del s by del s constant v, del u by del v at constant s. Okay. And this must be equal to del by del v constant s, del u by del s constant v. Now, if you look at this term, if you look at the expression in differential form, del u by del s at constant v is nothing but t, and del u by del v at constant s is nothing but minus p. So, this is nothing but minus p and this is nothing but t. So, I have now the relation minus of del p by del s at constant v. This must be equal to del s by del v at constant s. Okay. So, this is the first Maxwell relation which we have just derived, and in this case we have considered a closed system. Okay. If it is a open system, what we are going to do is we are just going to add n in this set of constant, okay. The relation still remains the same. Okay. So, this is the case for a open system. Okay. Now, you can also take an inverse and also can write it this relation in the following way: del S by del P minus as del V by del T. So, you can also use these inverse relations. Okay. So, we have now first relation which comes from the internal energy expression in the differential form. Now, I can consider other relations and try to develop. So, this yielded the following: this is minus del P by del S constant V is del T by del V constant S, and here we need to find it out. We can do the same exercise for del H here. So, this is we are going to do del H by del S del P, because H is a function of S and P, is nothing but del square H del P by del S. Okay. I can now write this as following. This can be written as del by del P and del H by del S. This is constant P, this is constant S, and del H by del S is nothing but, if you look at the differential, del H by del S at constant P is nothing but T. So, what we have is this as T. So, essentially I can write del T by del P at constant S. Okay. Similarly, here I can write here del S by del S constant P, del H by del P at constant S. I go back to the differential expression here, and del H by del P at constant S is here, del H by del P at constant S is nothing but V. So, we have now expression of here, this is equivalent to saying del V by del S at P is equal to del T by del P by S. Okay. So, this is the second expression. Okay. And then similarly we can get it similarly from the expression of A and G, we have the following expressions, and this is not so difficult to see that. If you look at it, del V by del S is del T by del P. So, essentially this is del V by del S at constant P is del T by del P at constant S, right. That is the expression we got. Okay. We can inverse this also and create a del S by del P. So, if you look at it here, what I have done is I have taken this in conjugate variable here and the differential of this with respect to dP at keeping S constant, that must be same as del V by del S at constant P. Okay. So, if I use similar exercises, I can actually get two more relations. One is this, I can write here as del S by del V at constant T, this is equal to del P by del T at constant V, and since this both has negative sign, it will cancel here, and similarly I can get here is del S by del P at constant T, this is nothing but del V by del T at constant P with a negative sign. Okay. Right. So, these are the four relations which I can obtain from this differential form. Okay. So, that is the four Maxwell relations we have obtained. Now, let us look at the problem which we have ended before the start of this lecture. Earlier we wanted to have this delta U to obtain from the state point going from T1 V1 to T2 V2. Okay, and we considered this as is equal to function of V. Right. So, earlier we wanted to have this relation of delta U going from T1 V1 to T2 V2, and we did this exercise and we ended up with this expression where we were stuck with this partial derivative of S with respect to T and partial derivative of S with respect to V, and that is why we wanted to say that, well, we must come up with an expression where we can change this partial derivative to something related to PVT and other relations properties which we can calculate from the experiments, and that is where the Maxwell relations come. So, if you look at this del S by del V, I can now make use of the Maxwell relation, because del S by del V, if you look at it here, del S by del V here is nothing but del P by del T at constant V. So, this expression I can write it here is delta U, which was there in T1, T2, T del S by del T at V is equal to V2 Tt plus V1 V2 T delta S by del V T is equal to T1 minus P T is equal to T2, okay, T is equal to T1, and this was the expression which we ended in the last class. Now, this by definition is CV, okay. CV is by definition is T del S by del T, and this from Maxwell relation, as I mentioned, this part is nothing but del P by del V. So, this is something which we can now calculate from the experiment. We can keep the temperature fixed and find out the change in the pressure as we change the volume, or the other way around. And then our expression in the differential form, not integral form, would be Cv dt plus T, and this term here del P by del V at constant. So, del V by del T at T should be del P by del V, del S by del V at constant T should be del P by del V at constant V. So, this must be at constant V minus P dV. Okay. So, this is the differential form here. Now, in addition to this Maxwell relation, as I said, we are going to make use of other thermodynamic properties or the variables, and one of the important variables are isothermal compressibility and the coefficient of expansivity. Many times it is because of isothermal, we symbol is K, and T is to identify that it is basically at a constant temperature, and this is 1 by V del V by del P, because you are trying to look at what is the rate of compression as you change your pressure. That means basically the amount of the volume which is changed as you change the pressure at a constant temperature, and the negative sign is meant because is added because this would be negative. Here the K must be positive, and this is something which we would like to prove it also later for stability analysis I was doing when we are going to talk about stability of the system. In addition to this, we would be also interested to have this variable, because we can calculate this in the experiment, coefficient of thermal expansion or expansivity. And many times this is also called volume expansivity. Usually symbols alpha is used, sometimes or beta is also used. Okay, so alpha or beta could be used here, but the meaning remains the same, that you are looking at how the volume gets affected as you change the temperature at a constant pressure. Okay, and it is important variables which you use. So, in addition to your beta k, you have of course Cv. Cv is del u by del t V is equal to T del S by del T at V, and Cp is del H by del T at P. So, this is per mole or per unit mass, and this is del Ts by del T at pressure. So, this is by definition. Okay. So, again let me summarize the Maxwell relations. So, we have obtained 4 Maxwell relations. Okay, summary of Maxwell relation. Okay. From the expression u du is equal to T ds minus P dV, and the Maxwell relation is minus of del P by del S at constant volume, this must be equal to del T here by dV at constant S minus sign is there because one of the coefficient of this here is minus. Okay. Then you have this function h, which gives you dH is equal to T ds plus V dP, and from here I can get del V by del S at constant P, this is equal to del T by del P at constant S. Okay. Then we have function A. Okay, sometimes people use F also, but let me just use A here, minus S dt minus P dV. Okay. And here I have del P by del T at constant V is equal to del S by del V at constant T. Again negative signs here gets cancelled, and so you have this relation, and then finally we have G, del G is equal to minus S dt plus V dP, and this is del V by del T at constant P, and this is negative here, this is equal to del S by del P by constant T. Okay. So, these are the 4 important relations which we have. Okay. Now, having derived these expressions, now let us try to do some examples making use of this Maxwell relation in order to simplify the expressions or the changes in the thermodynamic variables in terms of something which we can calculate experimentally. Okay. So, one of the example could be let us say this is an example, and so the question is to derive this expression. Okay. So, this is the expression here. So, here of course beta is the same as volume expansivity. So, let us start with du is nothing but T ds minus P dV. Okay. In this case what is being given as u as a function of, in this case if you look at the expression, independent variables t and v. So, I can write u also as du as du by dt at constant v, dt plus du by dv at constant t dv. Okay. So, this is, we know this is Cv dt, but what about this? Okay. So, let us try to derive this del u by del v expression. Now, this we have to go back to this expression here. So, because we want to find out del u by del v, and hence we are going to differentiate this with respect to v at constant t. So, that is your left hand side, because it is a constant t, we have del s by del v here, and then p minus del v by del v at constant t, this of course is 1, del v by del v is 1. So, what we have is del u by del v at constant t, this is t del s by del v at constant t minus p. Okay. Now, again we have an expression which is just a derivative of s with respect to v, and this we would like to write it in terms of something what we can evaluate in experimentally. That is why this term is something which will come from this exercise. So, we can try here now to make use of Maxwell relation. So, Maxwell relation, if you look at the Maxwell relation, del s by del v at constant t, del s by del v at constant t, okay, it is not there here at this point, right. So, what we can do is del s by del v is constant t. So, if you look at here, if we go back to the Maxwell relation, you have this del s by del v at constant t. Okay, so del s by del v, so it should be here. Okay, so this must be same as, so if you use this expression, this is, you can replace this by del p by del t at constant v. So, if you, this is equivalent to saying del p by del t at constant v. Okay. That means I have this expression on the right hand side as del P by del T at constant V minus P. So, I can replace this expression by this, okay, and still we can evaluate this expression by doing a certain set of experiment, but since the question is being asked to convert it into this beta and k, we must now make we must now try to use the definition of that and see if we can get the expression beta and k out of it. Okay. So, let us first write down again the expression of beta is 1 by V del V by del T at constant P, and k is minus 1 by V del V by del P at constant T. So, certainly none of these directly can be replaced here. So, but what we can clearly see is that PTV is part of these expressions, hence I can now try to make use of the minus or the chain rule, which chain rule says that del P by del T V and del T by del V P del V by del P T must be minus 1, or now here I can del P by del V can be written as minus 1 del T by del V P del V by del P T. So, now we can replace this by this two term, and these two terms are found in the expressions of beta and kappa. Okay. So, this essentially can be rewritten here in the following way. This I can bring it to the numerator. So, it's can be written as this minus divided by del V by del P at constant T, and this is nothing but del V by del T by constant T is beta V, and this is del V by del P T is kappa V with a negative sign, this is negative sign. So, this is nothing but beta by kappa. So, I have now a relation of this del P del T at constant V is nothing but beta by kappa, and hence I can write now du as Cv dt plus T beta by kappa minus P dV. So, that was something which we wanted to derive, and this is what we have it now. So, one of the way you can clearly see that it's difficult to remember all of these expressions. So, if you can see this derivation, you can understand how it has been derived, and hence you may not remember it, and you can clearly write in this differential form and evaluate, or and just write down the Maxwell relation based on this. So, the idea is to see the conjugate variables of the independent variables here for the corresponding equations, such as here let us say u. So, here for the case of u, what I did is I took the differentiation of p with respect to this at a constant v, and that must be equal to differentiation of t with respect to v at constant s. Of course, there is a negative sign, hence negative comes into. So, you can write down this, but there could be other ways which you can remember if you want to do that, and one of the often used approach is something called bond diagram. Okay. The way it is written or it works is the following, that you draw this kind of a square, okay, such that you have this S, V, T and P, which is corners of this square, and then you can draw these two lines, which one going from S to T and the other going from P to V, and this are the independent variables. Okay, so appropriate thermodynamic functions can be added now. H is for S and P, and if you look at T and P, this has to be G. If it is V and T, then this is A. If it is V as S, is nothing but U. Okay. So, what we have done is we have written something like this, and now you can write down the, let us say, thermodynamic function also in the following way. Let us say if a generic thermodynamic function is phi, then this is nothing but a sine of coefficient multiplied by the differential of independent variable. Okay. Right. So, you can demonstrate this. So, let us consider, let us say d of g. Okay. So, g has independent variables t and p. So, this is your dt and this is your dp. So, that is part of it, and then you need to have a sign of coefficient. So, the coefficient sign are written in this way. So, essentially for t the conjugate variables goes to s. So, essentially here I am going to write as a minus of s, okay, plus from p it going from p to v, but since it is going from originates from p in this direction, this is a positive. In this case we had written negative because it is coming towards t, and hence it is written minus s. Okay, that is what the sign stand for. So, sign and here it would be your, for p it is v. Okay. Similarly, I can write here d of h here. Okay. So, it goes toward from both the corners or both the vertices, and hence is going to be positive. So, here I can write ds, okay, with t here plus p, and this is Vp. Okay. So, this is by definition ds, and similarly you can write the other terms. Now, since our interest is basically to get the Maxwell relations from this diagrammatic approach, let us look at how it can be done. So, the idea is the same. You write it in this small thing S V T P, okay, right. So, this is how it is written. Now, when you look at from here, from the one of the sides, okay, then essentially what you have to do is you have to look at the edges, okay, here. For example, in this edge you have a V and S, and the corresponding vertex is here, which is connected to S because you are looking from it. So, essentially you can write it here as del V by del S, okay, keeping this P constant, and similarly this would be your edge here, del T by del P, but the corresponding the other side is S here, okay. And since both the arrows are towards the other side, and hence it is basically there is no negative sign here. Similarly, so until I show you the other examples, you will not be clear. So, let me just demonstrate it for the other side. Okay. So, now we are looking at from this side, right. So, this side has two edges here, one, and this is the one, this other one is this. So, it is going to be del V by del T, this must be equal to del S by del P. Okay. Now, if you look at it, what should be here in the constant? For the case of a del V by del T, it should be P. For the case of del S by del P, it should be T. Okay. But the other thing is that whether it is going to be positive or negative here. So, if you look at it from here again, one of them is approaching towards the edge. Okay. So, hence there has to be some negative. You can put it here or here, does not matter. Okay. Now, let us look at the other sides also. So, we put it here. So, this is going to be del S. So, this would be del S by del V should be equal to del P by del T. Again, del S by del V should be, the constant is T, for this constant is V, and both the sides, both these arrows are pointing towards this, hence this will be positive. Similarly, I can do the last one. So, this is your del T by del V, del P by del S, okay. These are the two edges, okay, 2 points here, del T by del V, del P by del S, and now for the case of del T by del V, we have kept S as constant. For the case of del P by del S, the V is constant, but if you look at from this side, one of the arrow is pointing towards itself, so there has to be negative sign somewhere, okay. So, these are the four Maxwell relations which we have evaluated from the bond diagram approach, which could be very useful if you are not able to understand or directly extract it from the thermodynamic expressions the way I was trying to do that. Okay. But I will try to show you another way to solve problems or remember this Maxwell relation, that will be your Jacobian approach, and I will take that approach in the next lecture. So, that will be the end of today's lecture.